So the last topic that we are discussing in the context of transistors is the transistorized differential amplifier. Before I say anything about this, let me just draw the circuit and then it will become easier to discuss it. So this is RC1, and here I'm going to give it some input signal, some AC input, let's call it Vn1. And now on the other side is essentially a mirror image of this thing. With input Vn2, and here at the bottom I'm going to put my emitter resistance. Sorry. Here is minus VEE. So think of it as two transistor circuits stuck to each other, facing each other in a symmetric manner. There are two inputs now, Vin1, Vin2. There are two sources of biasing. So there is the VCC over here, and there is a negative minus VEE over here. Now, for this kind of amplifier, as the name suggests, it's a differential amplifier. So we want to look at some difference. So the input over here is Vin1 minus Vin2. The output over here, so here are the two collectors. So this is the potential at the collector of the first. This is the potential at the collector of the second. And it's across these two that I am going to take the output. So the output, well, input is actually Vn2 minus Vn1 by convention. And output is similarly Vc2 minus Vc1. So the gain, which is output over input, is this. Okay. So the important thing to note over here is that as you increase Vin1, you will notice, and we have discussed this once or twice already, Vc1 will decrease. So when you increase the input at the base, then the collector voltage decreases, coming from the load line equation. But if Vc1 decreases, as you can see from here, the gain increases because Vc1 comes with a negative sign. So if you increase Vn1, gain increases. So Vn1 is called the non-inverting input. Oops. But what happens with Vn2? As you increase Vn2, Vc2 decreases. But if Vc2 decreases, then the gain decreases. So Vn2 is known as the inverting input. Now, this is the most general form of the differential amplifier, where you have two inputs, Vn1, Vn2, and output is also taken between two terminals, Vc2, Vc1. But that may not necessarily be the case. There are times when you only have one of your two inputs. So let's say you only have Vn1 and Vn2 is just set to ground. Or you might have just Vn2 and Vn1 is set to ground. Similarly, you can have cases where the output is taken between Vc1 and Vc2, Or you can also have cases where you only take the output at VC1 and not bother about VC2, or you take the output only at VC2 and don't care about VC1. So depending on how many inputs you have and how many outputs you have, you can have four kinds of differential amplifiers. You can have single-ended input, single-ended output, or you can have single-ended input, double-ended output, or you can have double-ended input, single-ended output, or you can have double-ended input, double-ended output. So this most general form that we have, this is a double-ended input, double-ended output. But if I didn't, let's say if I didn't have VC2 and I was only taking the output at VC1, so between VC1 and ground essentially, then I would call it a double-ended input, single-ended output. Or if I didn't have VC this one and this was just grounded, then this would be a single-ended input and a double-ended output. So these are your four kinds of differential amplifiers. We are going to look at one kind. We are going to look at the double-ended input, single-ended output. So what does that look like? Plus VCC, RC1. Actually, I'll take both of them to be the same. RC. And the output I'm going to take over here at the collector of the second one. So V out. So this is my double-ended input, single-ended output differential amplifier. Once again, in order to analyze this, I'm going to use the superposition principle. So first we will set all the AC signals to 0 and do a DC analysis. And then after that, we will set all the DC signals to 0 and do a purely AC analysis. So in the DC, it's very straightforward. All the AC signals to 0. So basically there is no AC input. This goes directly to ground. Now what should we do? You see that the base voltage is 0. So the emitter voltage, which is base voltage minus VBE, is going to be minus VBE. So that is the voltage over here. Base, collector, emitter. I'm doing it on one side, but because this is a symmetric circuit, the same thing also applies on the other side. Now since I know the emitter voltage, I can find out what is the current flowing through the emitter resistance. This part of the circuit is called the tail. So the tail current IT is VE minus VEE divided by RE, but VE is minus VBE, minus VEE over RE. Now remember that VBE is something like 0.7 volts. VEE is some DC biasing voltage that you're putting. So it's going to be something like, let's say 10 volts, 15 volts, something like that. And it's negative. So this is going to be something, just to give you a numerical example, this is going to be minus 0.7 minus, and because VEE itself is negative, minus 15 over RE. So like 14.3 over RE, something like that. So basically it's a positive value of the current which is flowing downwards through the tail. How far can you see? Okay. What have we done? We got the tail resistance, the tail current. Now, the current that is flowing through the emitter, so over here and over here, from symmetry it is going to be half the current in the tail. So IE is IT divided by 2. So now we know what the emitter current is. And therefore we know what the collector current is. And if you want to write down the load line equation, then VCC is going to be equal to ICRC plus VCE plus VBE plus VE. Normally we write VE as IERE, but I've written it VE for the following reason. I can now write this as ICRC plus VCE, and VE is minus VBE. So VCC we know, VBE we know, RC we know, IC we know. So we can find out what VCE is. Now it's time to go for the AC analysis. So again, same way of doing of drawing the AC equivalent circuit, which is you set all your DC sources to 0 and you make all your capacitors shorts. In this right now there are no capacitors. Of course, this is the most basic, most rudimentary kind of differential amplifier that we can discuss. In general, when you make a real differential amplifier which can be used professionally, then there will also be some internal resistances in that. So RC, there was supposed to be a plus VCC over here on top, but AC analysis, so that has to go to ground. And I'm going to put some VN1 AC input, VN2 AC input. Now I can again do that simplification, the T model kind of analysis, where I'm going to replace my transistors with a constant current source at the collector and an RE prime resistance at the emitter. So this is equivalent to and output is being taken over here, just to remind ourselves. Now for this transistor, let's put one IC, RE prime. Same on this side, IC V into RE prime. And over here you would put an RE, and there is a minus VEE, which is a DC source. So again, that goes to ground. Now, normally the value of RE that we have over here is much larger than this RE prime. So any current which is flowing through these emitters will just mostly flow, any current flowing this way will just keep flowing this way. Almost none of it will go through RE because RE is very large. So for all practical purposes, this part of the circuit is as good as not there. Okay. Now, once again, we are almost done with our analysis. If you apply Kirchhoff's voltage law across this, what you get is V in 1 is IE. So let's call this current IE. IE RE prime. The same current is flowing also into the other RE prime. So again, plus IE RE prime plus V in 2. So V in 1 minus V in 2 is twice IE RE prime. And then, where am I taking my output? Output is over here. The output, there is also a ground over here. The output is just the potential difference across RC, because there is the ground over here. So V out is just IC RC. So the voltage gain, which is V out over V in, is ICRC divided by twice IERE prime. But once again, we know that IC and IE are roughly the same. So for a differential amplifier, the voltage gain is RC divided by twice RE prime. So if you know what your collector resistance is, and if you know RE prime, how do we know what RE prime is? Once again, same way as before, RE prime is 25 millivolts divided by the DC emitter current. So you know all these quantities, you know IE from the DC analysis, you know RC based on what your circuit is built. So this tells you what is the voltage gain. You can also define what is called the input impedance. See, input is what is happening between V in 1 and V in 2. So the input impedance, which is referred to as Z in, can you see? So this is the total input voltage divided by the total input current. Input voltage is twice IE RE prime, just the difference between V in 1 and V in 2. The current that is flowing in is the base current, IB. But IE divided by IB is beta. So this input resistance, input impedance is twice beta Re prime. Now remember that beta is typically a large number, 100 or more. So the input impedance can be quite large. What is the advantage of using a differential amplifier? A differential amplifier, it measures the difference between V in 1 and V in 2. Now, sometimes what happens is when you are trying to compare two signals like V in 1 and V in 2, and let's say you want to amplify the difference between them, sometimes in your signal you don't just have the required signal, you also have a large amount of noise. You have some unwanted signal coming in. It could be some stray electromagnetic signal, some radio noise, whatever it is, some kind of unwanted component to your input signal. Now, because your differential amplifier is taking the difference between V in 1 and V in 2, these noises cancel out, because noises typically will be the same in both places. If there is some ambient electromagnetic stray signal in the room, that is going to be the same at both of your terminals. So the advantage of using a differential amplifier is that all of these noises cancel out. If you're using just a single-ended amplifier, then the problem with that is that it will pick up your signal, but it will also pick up your noise. It will amplify both of them. Now, because you're taking the difference, the noise part cancels out and you're only amplifying your required signal. So that is one of the advantages of a differential amplifier. And there is a way of quantifying it. What you can do is you set V in 1 equal to V in 2. So basically the signal is the same in both. There might be some background, some small background, and then you can see what is the gain in this case. So this kind of setting, when V in 1 and V in 2 are the same, this is called common mode. And then you can define the common mode gain. So ideally, of course, the background is the same in both input 1 and input 2. So the common mode gain should be 0 because there is nothing to amplify. But in reality, there will be some small non-zero value of this common mode gain. So ideally, ACM is 0. And then what you do is you take your normal usual gain or differential gain, AB. So this is what you normally do when you have a differential signal between input 1 and input 2. And then we define what is called the common mode rejection ratio, or CMRR, which is defined as AV divided by ACM. So ideally this should be infinite, because ideally common mode gain is 0 and the differential gain is some non-zero large number. But in reality there is some small value of ACM. So CMRR will not be infinite, it will just be some large number. And the larger the value of CMRR, the better is your differential amplifier, because it means it is that much better at rejecting background signals, background noises. So this is the common mode rejection ratio. You can also define common mode rejection ratio in decibels, and that is defined as 20 log 10 common mode gain over differential gain over common mode gain. So this is how you define CMRR in units of decibels. Differential amplifiers are very useful. For the next 2 weeks, we will look at a number of circuits using differential amplifiers. In fact, even in your everyday applications, if you look at uh, the whole USB system of transmitting signals, USBs use differential gains in order to take just the signal that is required and reject backgrounds. So this concludes our discussion of circuits involving transistors. And next lecture onwards, we will start discussing operational amplifiers or op amps.